Hi all, welcome back to Ashkimi. So today we'll have the third part of the question paper discussion of a Kerala PSC exam that was recently conducted for multiple posts like work assistant, assistant chemist, etc. So without wasting much time, we'll move on to the first question. So let's have the first question of this video, which is question number 11 of the question paper. Which among the following is an organometallic compound? A. Lithium methoxide, B. Lithium acetate, C. Lithium dimethylamide, D. Methyl lithium. So for that we have to understand something regarding organometallic compound. The basic criterion of a compound to be an organometallic compound is that it should possess a metal carbon bond. So metal can be anything, any metal you can have, but the compound as such, it should possess at least one metal carbon bond. So we'll have a look at each options whether they are having a metal carbon bond. Let's consider the first option, which is lithium methoxide. Okay, lithium methoxide. So in the case of lithium methoxide, methoxide is an alkoxide ion, say CH3O minus. This is methoxide. So this is a negatively charged ion. So in order to stabilize that, you need a positive ion, which is lithium ion. So this is the structure of lithium methoxide, or else you can write it in the form CH3OLi. So probably you will be having a oxygen lithium bond, but the carbon atom is not bonded to lithium. So you can rule out this option because it's not a organometallic compound. Now moving on to option B, which is lithium acetate. So you know that acetate anion, this is acetate ion is an anion, that is CH3COO minus. It's the carboxylate ion corresponding to acetic acid. So this is a negatively charged ion. So you need to have a positively charged ion for balancing the charge. So that is lithium plus. So here also you are having a oxygen lithium bond and you are not having a carbon lithium bond. So you can also rule out this possibility. Now moving on to the third option, which is lithium dimethylamide. Dimethylamide. So amide is an anion which is generated from ammonia. So when you are removing a hydrogen atom from ammonia or a proton from ammonia, you will get an ion called known as the NH2 minus, and this is known as the amide ion. So when you are replacing this hydrogen atom with a methyl, you will be getting dimethylamide. That is, instead of two hydrogen atom, if you are having methyl group, you will be getting the dimethylamide. That is also a negatively charged ion. So it is balanced by a lithium ion. So when you consider this particular compound, this compound is having a nitrogen lithium bond. Here also you are not having any lithium carbon bond. So you can also rule out this possibility. Now moving on to the last option, which is option D, which is methyl lithium. Methyl lithium is actually a derivative of a alkane. So here the alkane happens to be the methyl group. You know that methyl group is nothing but it is CH3. CH3 minus you can say, and that is coordinated to lithium. This is actually the structure of methyl lithium. So when you see the structure, it is quite clear that you can have a lithium carbon bond, and the actual structure of a methyl lithium is an oligomeric structure, which is shown in this slide. This is actually the structure of methyl lithium. You can say that it is having somewhat a cubane like of structure with alternate corners containing lithium and methyl group, and each carbon atom is attached to three different lithium ions. So this is actually the structure of methyl lithium. That's a very important structure in exam point of view. Many questions are asked from this part, so you have to by heart the structure. So it is having a cubane like of structure or an oligomeric structure where each lithium each methyl group is coordinated to 3 lithium atom. And similarly, each lithium is coordinated to 3 methyl groups. So this is actually the structure of methyl lithium, which is having a carbon metal. Lithium is a metal, so there is carbon metal bond. So this satisfies the criteria for an organometallic compound. Therefore, the correct option is option D, which is methyl lithium. Okay, that's all for this question. Now let's have the second question of this video. When excess of ammonia solution is added to copper sulfate solution, dash is formed, and you are provided with 4 different options. So this is a complex containing 2 ammonia ligand, and this is a copper complex containing 4 ligand, probably maybe having a tetrahedral type of structure. So here also you are having a tetrahedral type of complex, and here again you are having a tetrahedral type of complex, but the charges are different. In this particular case you are having a positive charge, uh, and in this particular case it is the ligand is somewhat different. It is ammonium ion instead of ammonia, but 4 ligands are there. Here also you are having 4 ligand, but the charge is different. Copper is +2 in copper is in +2 oxidation state, whereas in this particular case it is in +1 oxidation state. So let's have the answer for this question. So normally when ammonia solution is added to copper sulfate, so and that too in drop by drop manner, ammonia ions will be completely reacted with this copper sulfate, and it would precipitate this copper hydroxide. So when you are adding ammonia dropwise to copper sulfate solution, it will be forming copper hydroxide, which is actually formed as a precipitate, and ammonium sulfate is formed as a byproduct. So this is the reaction that normally take place when you add ammonia drop by drop to copper sulfate solution. But when you are adding excess of ammonia to copper sulfate solution, then the precipitate will be different. That is, the precipitate so formed will be dissolved in ammonia, and it will form a soluble complex, that is copper sulfate plus 4 ammonia molecule forming CuNH3 4 times sulfate. So when you look at this particular complex, the charge of this complex is +2 because the sulfate ion is having a charge of -2. So in order to balance that, this coordination sphere, it should have a charge of +2. So the correct option is CuNH3 4 times 2 plus. This is the structure of the complex, or the stoichiometry of the complex, which is formed when excess of ammonia solution is added to copper sulfate solution. So the right answer is option D. Okay. Now coming to the succeeding 3 questions in the question paper, some error is found either in the question or in the option. So I hope this will be deleted when the final answer key appears. So when you consider the 13th question, it was about to find out the correct name of a complex, that is nomenclature of a coordination compound. And it was an oxalate complex of aluminum, but none of the option correspond to the actual name of this complex. So this might be deleted. Now coming to the 14th question, it is about the spectral data of a compound is given, and you are asked to find out the correct structure. But here the molecular mass 112 given can correspond only to option A and B, but none of the compound in these two options can give a NMR signal in the aromatic region, that is at 8.48 delta. So none of the option can correspond to the answer to this question. Therefore, this might also be deleted. And coming to the 15th question, there is some typos in the question. That is, the complex given, both of the complex given are the same. Therefore, this is also having some problem with the question. Therefore, this will also be deleted, I suppose. So we'll have the next question, which is probably a question from metallurgy. The method of electrolytic refining is not suitable for the extraction of aluminium, copper, mercury, and silver. In order to answer this question, we need to have some idea regarding the electrolytic refining in extraction chemistry. Electrolytic refining is a method that is usually used for the extraction of metals. Okay, like aluminium, copper, gold, silver, platinum, etc. So in this method, you'll be using the same metal, that is the metal to be extracted, the pure form of that metal as cathode, and the impure form as the anode. And you'll be having a electrolytic solution also, which is made of the same metal. That is, if you want to extract copper metal, then copper sulfate solution will be used as the electrolyte. So in the beginning of the extraction, you can see that the size of the anode will be large, which is the impure copper, and the size of the cathode will be small, which is made of the pure copper. And when you pass electricity through the cell, what happens is that uh, copper from impure copper will be oxidized to copper 2 plus, and that will be going into the solution, and finally it will be coming at cathode and it will be reduced to copper, that is Cu2 plus will be reduced to copper. So when you look at anode, copper will be oxidized to copper 2 plus, and at the cathode copper will be reduced to copper 2 plus will be reduced to copper. So this is what is taking place during the reaction. Now as time elapses, you can see that more and more amount of copper from anode will go into the solution and will be finally reduced at the cathode. And the other metals or other impurity that is present in this anode, that will be settling beneath this anode as anode 1. So finally, when you look at the cathode, it will be having only pure copper. Okay, so that can be, and moreover, the size of this cathode will be increasing, and finally, you will be having a rod of pure copper. So this is how the purification procedure or the extraction procedure is carried out for this metal copper. And similarly, you can also have other metals like gold, silver, platinum, etc. But from this option, it is well clear that mercury cannot be extracted using this method, because mercury is a liquid. It is not a solid. So it cannot naturally form the anode and cathode. So normally we cannot use this method for mercury. Therefore, the correct option is option C, which is mercury. Okay, that's all for this question. So let's move on to the next one. The next question is about biological function of two enzymes, carbonic anhydrase and carboxy peptidase. So you are provided with 4 options and you have to correctly find out the functions of carbonic anhydrase and carboxy peptidase. So both these are zinc containing enzymes which perform different roles. If you consider carbonic anhydrase, it actually hydrates carbon dioxide to form carbonic acid. So this is the reaction that is catalyzed by carbonic anhydrase. So when you consider the structure of carbonic anhydrase, it is like it is having a tetrahedral structure with zinc as the central metal ion. That is, you are having zinc in the center, and there are 4 different ligands. The first ligand is a water molecule, and after that you are having 3 histidine residues. That is, nitrogen atom of histidine residue is coordinated to zinc. So this is the structure of carbonic anhydrase. So when you look at the mechanism by which this carbonic anhydrase catalyzes this particular reaction, this is the mechanism. So initially the mechanism begins with the deprotonation of the water molecule that is coordinated to the zinc. So it will lose an H plus to form a hydroxide ion. Okay, after that, in the second step, the carbon dioxide, which is the substrate molecule, that is being added, and that will react with this hydroxide ion and will be getting coordinated to zinc. And in the fourth step, finally, the carboxylate, the HCO3 minus ion will be eliminated, which can combine with a proton to form the H2CO3. So this is a 4-step cycle by which this carboxy anhydrase, carbonic anhydrase catalyzes the conversion of carbon dioxide to carbonic acid. That is interconversion of carbon dioxide and carbonate. So that is the function of carbonic anhydrase. Now coming to the enzyme carboxy peptidase, which is again a zinc containing enzyme, which is also having a tetrahedral structure like the carbonic anhydrase, with the zinc as the central metal atom. It performs the cleavage of polypeptide, especially the C terminal of the polypeptide chain to form a polypeptide chain with the reduced residues. Okay, so this is the function of carboxy peptidase. Now, when you look at the structure of this carboxy peptidase, it is like it is having zinc in the center, and again the three ligands are the same. There are water molecule and two histidine nitrogen atom that is coordinated with the zinc. The third one is a glutamic oxygen, that is oxygen atom of a glutamate residue. So this is the structure of carboxy peptidase. When you look at the mechanism by which this carboxy peptidase cleaves the C terminal of an amino acid chain, initially it will coordinate with the amino acid chain, the C terminal of an amino acid chain, and it removes this amino residue, and after that it again coordinates with the carbon atom of the C terminal chain, and it will coordinate with that, and from that the C terminal group is removed as carboxylic acid. So the again the active part of the enzyme will be regenerated, which again adds to the C terminal of the amino acid, and the process can continue till desired amount of C terminal amino acids are being removed from the polypeptide chain. So this mechanism is somewhat complex one compared to the mechanism of carboxy anhydrase. So you need not by heart, but you can just have an idea regarding the mechanism. And mechanism of carbonic anhydrase is very important. So if possible, you can by heart the mechanism. Okay. Therefore, the correct option for this particular question is option D, that is carbonic anhydrase is involved in the interconversion of carbon dioxide and carbonate, whereas the carboxy peptidase A is involved in the hydrolysis of peptide bond or cleavage of peptide bond or removal of C terminal amino acid from a polypeptide chain. So that's all for this video, and if you find it useful, please do like, subscribe and share, and I'll be coming soon with the fourth part with the other questions of this question paper. So till then, take care and bye bye.